Welcome back, ladies and gentlemen. I'll be going through some of your notes from your booklet, so make sure you have it out there. The fact that we have printed booklets makes this a lot easier. We're going to start off on page 6. It's going to look like this, although yours is not in color. I'm sorry. Color is a little expensive. All right, so we've started off yesterday, or last time I should say, on our review of grade 10. And we're going to continue, because it's been a while for some people since they did grade 10. I mean, for all I know, you guys could be taking this in your grade 12 year. Could have been 2 years away. So it's no big deal if you don't immediately remember absolutely everything that I'm talking about. That's why review exists. And that's one of the nice things about videos. You guys can look them up whenever you want. But let's start by filling in some of our notes. So it says here that ion is a charged particle. An ion is formed when a neutral atom gains or loses electrons. Positively charged ions have one name. Call them cations, and a negatively charged ion is called an anion. Let's make it plural. Now, I have heard cations pronounced a few different ways, mostly by Latin-based languages. French speakers especially will want to call that a cation. It's not, it's a cation. And one of the things you can do in order to remind yourself which one is positive is that you remember that cats have paws. I know, it's bad. The general rule when it comes to science jokes is that they're not funny, so you're not allowed to laugh at them. But you are allowed to groan. If you don't groan, that probably means you need to study a little more. So, cations are generally positive, anions are generally negative. Now, we talked a little bit about atoms yesterday. We reminded ourselves about the periodic table, about how all of that is designed, all of those things. So now we're talking about ions. And what you can see on your page there, on page 6, is that you've got a sodium atom, and that atom has got an electron in the outer valence, and then it loses it. That extra electron pops off. So if I very quickly sketch it here, we have Na, and it's going to have some electrons. Hopefully you guys remember your Bohr diagrams. And if this outermost electron pops off, right, if it leaves, if it disappears, well, then I've made an ion because I have removed an electron. The atom is no longer neutral. It is no longer neutral. It now has a charge. But the question is, what charge does it have? Well, the way we do this, as a reminder here, right, is that we have to compare the number of protons and the number of electrons. Oh, come on, I have colors. Why am I? See, I said color was expensive, and then I'm going out of my way to use nothing but black and white for you guys. Come on, let's do some colors here. So, protons and electrons. So, how many protons are in sodium? Well, I mean, the sodium Mr. Cedrew is wrong, so that doesn't help. 2 in the middle here. So, how many protons in sodium? We can look it up on our periodic table, which you should have a copy of. And you're going to see that there is 11. Why 11? How do I know? Well, because remember, atoms start off neutral. There were originally 11 electrons here, so there was 11 protons, because neutral means that the two of them are balanced, as we discussed previously. Well, okay, great. So we've got 11 and 11. Oh, wait, no, we don't, because I took one away. I removed it. So that means there isn't 11. Now there's 10. Okay, so we're 1 short. But electrons are negative. And protons are positive. So if I take positive 11 and I subtract 10 from it, I'm going to get 1 plus. You may remember from grade 10 that we write in chemistry our numbers as 1 plus, not plus 1. That's just because we want to be different from math. Okay, that's not the only reason, but it's the main thing that you're going to have to worry about. So we see here that this ion is a positive ion. So, based on the incredibly terrible joke, that means this must be a cation because it is positive. Okay, well, that's cool and all, but, grade 10, we did a little more than just make ions. What else did we do? Well, take a look what it says. Ionic compounds are formed when two or more oppositely charged ions are attracted to each other. This chemical attraction is called a bond. An ionic bond is formed when a negatively charged ion is attracted to a positively charged ion. Ions combine together so their charges make 0. So in this case here, this guy's a 1 plus, so I can put 1 plus up there. Well, that electron that went spiraling off into space, maybe it got picked up by some fluorine. And if it did, that means that the fluorine would have gained an electron, right? So it has one more electron, while losing an electron made it 1 plus, so this one's going to become 1 minus. Well, opposites attract. This is a positive, this is a negative. So these two will come together. And in doing so, they will neutralize each other because you get a positive and a negative. Just like how it was originally positive and negative were equal inside of an atom, now the two ions combined make something that is equal as well. There's also, as it mentions down there in your notes, ionic compounds are usually made of a metal and a non-metal. Metal and a non-metal. Do we remember that? I hope so. We talked about it just yesterday. A metal is anything on the left side of the periodic table, and a non-metal is on the right. If I drew a quick sketch of a periodic table, let's see, well, you guys get to discover that Mr. C can't draw, but that's fine because I'm not an art teacher. There we go. There's our quick sketch of the periodic table. There's like a little staircase in your periodic table, and everything on this side is a metal. And everything on this side is a non-metal. Could we have come up with a cooler name? Totally. Did we come up with a cooler name? No, because as you will discover, scientists are really bad at naming things. They usually call it exactly what it is, and then they change it to a foreign language to sound smarter. But non-metal it is. So if I take something from this side of the table and I bring it near something from this side of the table, and they're ions, they will stick together. And that's what makes tons and tons of things. I mean, you, me, my keys. Take your pick. So that's a really brief example there, right? A reminder of how this all works. Hopefully that's ringing some bells. If it doesn't, that's fine. Feel free to ask me questions. I'm totally here for that. Now there's some examples here of some compounds, and they look like stuff like this. You could have NaCl, or you've got CuSO4. This, of course, is using chemical symbols or element symbols in order to write out the chemical equation. There's also the names of those chemical equations right next to it. This first one is good old sodium chloride. And the next one is copper sulfate. Now, we're going to have to review more of this. That's really what I want to talk about today. But, you know, a little bit of a refresher, right? Remind us of things. So, flip it over. On page 7 here, you're going to see you guys have some examples that you guys can work through, just of trying to, like, figure out what's the symbol, what's the name, what's the ion look like. Now, I did here sort of a quick Bohr diagram, but you guys would have learned last year a Lewis structure. So it looked something like this. And if I want to be fancy with extra colors, there you go. This is a Lewis structure named after a guy called Lewis, who was a student, much like you guys, who decided that drawing Bohr diagrams was an awful lot of work, and he didn't want to have to do that. So he found ways to take a shortcut. And what he discovered was that all the stuff on the inside of the atom doesn't really matter. For chemistry purposes, the only part that matters is the outside, the valence, if you remember that word from grade 10. So all this sodium here, all the stuff that we drew, I don't need it. I could erase all of this and it would still be pretty much accurate. So this is sodium 1+. And that obviously is a lot less work and less likely to have Mr. C make a mistake and forget to put in a couple extra electrons. Obviously, before it was an ion, when it was still an atom, it would have looked like this, with a single dot, because it had one electron that it then lost. Showing a missing electron is usually difficult. There's a couple ways to do it. Usually we just do nothing. That's one option. Also, I've seen people do it where they just show like a gap, like a hole or something, right? But really, I'm just going to go with like that. Okay, so if you guys give page 7 a try, that's fine. You can pause the video, give it a shot. I'm going to keep going, though, in this particular little description, and then you guys can just keep going as you're ready. So on page 8, we talk about binary or ionic compounds, like that one. And it says here, a binary compound contains 2 different kinds of elements. There can be more than one atom of each element in that compound. The binary compound usually contains one metal with one non-metal, one of those and one of those. Metal ions are generally positive because they're, cats, and non-metals are generally negative because they're not cats. When naming an ionic compound from its formula, we have certain rules that we have to follow. And you can kind of see the rules just looking at this guy right here. NaCl. Look what's first, sodium. Now if you look, sodium is on your table. Sodium is about there or so on the table. Okay, so sodium is clearly on the metal side of the table. So the first rule is that the metals, the cations, go first. Cats first, I guess you could say. Then you put the non-metal. Okay, so metal, non-metal, done. Then you're going to write the full name of the metallic element, full name of the metal, sodium. Sodium is its full name. Now, you may wonder why it is it's Na and this is sodium, and those don't seem even remotely similar to each other. That's because the Na here is based on Latin. And I don't remember what the Latin word for sodium is. I think it's nater or natrum. Yeah, I think it's natrum. There's a bunch of different symbols in the periodic table that don't seem to match English, and that's because they don't. So, for example, iron is Fe because it was originally ferrum, and silver is Ag because it was argentum, and gold is Au because it was aurum. So, a bunch of these don't really match, and that's because they were using a different language. Again, scientists will make themselves sound smarter by using a different language. Okay, so once we've got our metal in there, the next step is to write the non-metal, but there's a catch, because we can't just put like metal, non-metal and just write it as is, because then it would be too easy. Not quite. Because then it would be hard to tell if these are 2 ions or 2 atoms, and that's important, because atoms react. Ions kind of don't. So in order to mark that it is an ion, we end up changing the ending. And look at how we change the ending here. This is chlorine. Chlorine is about there-ish or so on the periodic table. Chlorine here turns into chloride. Right over here, we have an IDE ending. You may remember that from when you were in grade 10. We would have spent a lot of time talking about that change from chlorine to chloride. This, usually I talk about in grade 10, and I mentioned, fluorine, which is right there on the periodic table. It's the F, is the most reactive element on the table. We'll learn more about reactivity much later in the course, but it's the most dangerous, basically, right? Fluorine will react with just about anything. Fluorine is incredibly dangerous. Fluorine is so dangerous that chemists would refuse to interact with it. They will generally avoid doing it if they can. If something's like, oh, it's got fluorine in it, everyone's like, oh, fluorine, maybe we better take it easy on this one. Fluoride, IDE, is in your toothpaste at home. You put it in your mouth. Fluorine, chemists don't want to touch. Fluoride, you put in your mouth. I'm hoping you brush your teeth. The difference, fluorine, looks like that. It needs one more electron to fill its valence. It is desperate for that extra electron. It will do anything to get that extra electron, and by anything I usually mean beat up any other element it can get its hands on. Fluoride already has its electron. It is happy. It is full. It's gotten its meal. It is done. It's beaten up its quota of other elements. So it's safe. Heck, it's useful. It helps to protect your teeth and bones. So, that's it. That's how you do it. Metal, then non-metal. Change the ending to IDE. Let's try another one. Obviously, I know this one right here looks a little different. We'll get to that later. Some of you may remember it, but we'll get to it later for those who don't. No problem if you don't remember it right off the hop. So the other example here is MgP3. Oh, Mg3P2. I should read the question. What do you think? So metal is first. Mg is sitting about here-ish on the table, so that would be magnesium. And then P is about here on the table. You guys are going to need your tables. Make sure you have them. And that's going to be phosphide. Why phosphide? Because we changed the ending to IDE. And that's it. Do I care that there's a 3 and a 2 there? Do I have to write that in any way? No. Don't. Why? Because, as you may remember from grade 10, the ions follow a predictable pattern. As you guys did with the example questions on page 7, right? All of the elements that are here are one step away from the end of the race. They all want to gain 1 electron. All the ones next to it want to gain 2 electrons. Gain 3. They want to gain 4 or lose 4. And then here, I want to lose 1 to come back to this side. I want to lose 2. I want to lose 3. And then, of course, 4 in the middle with carbon. You can go either way. So there you go. That's the basic idea. You guys have done that before. You guys have seen it a few times. Now, page 9 continues to talk about this going backwards, right? So far we've gone from here to there, but sometimes we don't give you the formula. Sometimes we give you the words, and you got to be able to turn words into formulas. How does that work? Well, let's take a look at the examples we give you here, right? So the example says aluminum oxide. Okay. Aluminum. Aluminum is, of course, a metal. So when you don't have all the different symbols memorized, what you probably want to do is at least try to think and look in the right area. It's a metal, so there's no point in me looking at any part of the table I'm covering with my head. It's all got to be in this area because this is the metal area. So when I find aluminum, it's going to be right there, and it's going to be Al. Oxide is, of course, a non-metal, which means it's going to be on this side of the table. Much smaller area, easier to search. Oxide is, of course, going to be oxygen, right? The IDE ending. So, yay, we're done? Not quite. When we went from symbols to words, we didn't have to put anything with the numbers. But when we're going from words back to symbols, we do. Now we care about the numbers. Why? Well, broadly speaking, because these particular elements follow a very particular pattern in the table, chemists find it unnecessary to mention the numbers all the time, right? Like, I don't need to tell you sodium chloride is a 1-to-1 because anybody who knows chemistry would go, oh, yeah, sodium chloride, sodium is a 1, chlorine is a 1, this should be easy. An analogy would be like if every time you said something, you also explained what it meant, right? So you're like, hello, which is a greeting. I hope you are well, which is me wishing you good times. Explaining what you mean as you say it is a little redundant. It's unnecessary. Now, of course, the downside is if you happen to say, buonasera, and the person doesn't speak that language, they're going to be like, I don't know what that means. So if you don't know the language of chemistry, the fact that they don't explain everything doesn't help. For those who are curious, that meant good evening in Italian. So what we're dealing with here is a language, and it's been a while for some people since they had to do this language, which means it's going to be a little rusty, just like any language. But with a little practice, you'll get there. Now, once we get the aluminum oxide, the next thing we have to do is we have to write down their charges. So aluminum is here on the table, which means that it is 3 steps away from the end going left. Metals go left. So 1, 2, 3. There it is. So this guy's going to be 3 plus. Oxygen is about there, which means it's 2 steps to the end. So it's going to be 2 minus. So we've got 3 plus and we've got 2 minus. Now let's make that 2 a little bit darker so we can see it on film. 2 minus, much better. So remember, we need everything to balance to 0. That is when the reactions stop. Now, in grade 10, I usually showcase this. I will show this with diagrams, just like we saw up here. So if I do a quick diagram of this, I would get aluminum, which has 3 electrons on the outside, and I would have oxygen, which has 6 electrons, and it needs 2 more. That's why it's 2 minus. It needs 2 electrons. So this electron here will go right over there, and this electron will go right over there. So this oxygen is totally happy. It's gotten everything it needs in life. It has 2 extra electrons. It's now 2 minus. It's sitting happy. The aluminum is not so happy. It still has 1 it's got to get rid of. So what does it do? Well, it finds another oxygen, and it says, hey, oxygen, I'm going to give you this electron. And the oxygen's like, well, thanks, free electron. I love it. So that means this guy's now happy. And now this guy is, of course, a 3 plus, because he's given away 3 electrons. But now this oxygen is like, well, I've got 1 electron, but I really want 2 electrons. So where can I get another electron? I know. I'll find myself another aluminum, the gullible fool who will just donate me an electron for nothing. So an electron swings over, boom, this guy is happy. 2 minus. Oh, but look, the aluminum, it's not happy anymore. Oh, will it never end? It does end. Obviously, it ends very soon. At least I hope it's obvious. Maybe you can see the pattern. Another oxygen. I'm running out of space. See, I didn't make enough space when I do my diagram. This one here swings down. This one here swings over. We get 1. We get 2. This is 2 minus. It's happy. This guy's also happy because he's given away everything. Yay, everybody's happy. But what do I do with this diagram? How does this diagram turn into that? Very simple. AlO. How many oxygens? 1, 2, 3. How many aluminums? 2. There's the answer. Now, do you need to draw that every time? No. Heck, do you need to draw this every time? No. Once you've reminded yourself of the charges of the ions, once you remember how all of this stuff works, you can just run with it. I don't need you to draw all these things out. But it's been a while for some of us since we did the chemistry language, so I'm just showing all of the steps, all of the different ways. Now, usually when you're dealing with this, what you're going to want to do is do it a little bit quicker. There is a trick here, you'll notice. 2, 3. 3, 2. Oh. I'll bring the 2 down, I'll bring the 3 down, and I'm done. It's called the Criss Cross method. It's mentioned on page 9 there for you. All right, let's try another example. The next one here, it says, is barium fluoride. We'll put it on this side just so we have all of them on the same side. Barium fluoride. I should be more accurate. It should be lowercase b. So barium, we'd have to find it. It's going to be Ba. Fluoride is F. I remind myself fluorine is 1 minus. Barium, though, I don't remember that one off the top of my head. So I look it up on the periodic table. It's about here-ish, so it's 2 steps from the end. So this is going to be 2 plus. Okay, I could draw it out, obviously. Totally an option, always an option. Or I could crisscross it and just go, 2, 1. Okay, so it's going to be BAF2. Another way to look at it, if you don't want to crisscross it, is it's at the end of the day, it's just doing it in algebraic. It's math, right? This guy is 2. Oh, there. This guy here is 2 plus. This guy here is worth 1 minus. So I'm going to need 2 of the 1 minuses to equal the 2 plus, because everything has to equal in the end. Okay, so there we go. That was a brief review of all the things to do with binary, meaning 2, ionic formulas. I want you guys to take a look now on the next page, on page 10. You guys are going to see that you guys have some practice you can try, naming and writing formulas. Okay, so give that a shot, see what you guys can do. Next video, we'll talk about what's going on page 11, and we will talk about polyatomics. That's what used to be over here. All right, best of luck, guys, and I will see you next time.